Let's have this work. I'm live. Okay, we're all live. Okay, so I want to start off by talking about the homework. First problem is sort of describe your interpretations of this paragraph on Wikipedia, describing the result of some research at the University of Alberta to create essentially the perfect poker player, at least for the slightly simpler game of limit hold'em. And it says, stuff about a Nash equilibrium. Anyway, Nash equilibrium is a pair of strategies such that given the strategy of the opponent, you have no incentive to deviate from your strategy. And they've almost achieved that. So given the strategy Cepheus plays, strategy again is, or maybe for the first time, is a rule about what decisions you would make in every possible state of the game. And if you know that, you could devise a strategy whose expectation would have a slightly positive amount of chips against Cepheus. However, the difference is so small that you could play poker for an entire lifetime, and if you started with the assumption that these two strategies have an equivalent expectation, there's no amount of data a human could generate in a lifetime of playing poker against Cepheus that would be sufficient to change your mind as to the two expectations were equal. And this is a fundamentally frequentist claim because the expectations that they're talking about, or the distribution of the test statistic for a difference in expectations being zero, are taken or generated by an explicit randomization mechanism, namely shuffling of cards if you're playing poker physically, or sampling cards without replacement for a deck if you're on a computer. So these expectations are expectations with respect to a distribution induced by a specific randomization mechanism. And thus, there's no need to bring in Bayesian stuff to evaluate the claims made in Wikipedia about, you could get a slightly positive expectation or something like that. However, the Bayesian perspective, although it's not necessary for something when there's an explicit randomization mechanism, is still works fine because, if all you knew was like, okay, I'm going to roll a die and I think it's fair, your predictions, your expectations would be based on the probability distribution that each face comes up 1 out of 6 times. So if you say, okay, I have my beliefs about the die, but unless you're crazy or you have strong evidence that this is a loaded die, your beliefs about what the die is going to do should be the same as, essentially the frequentist. And the same thing here. So what is good, I think, about poker? Well, you might say, why are we doing a whole homework or half a homework, maybe 3/4 of a homework on poker, is not because we're learning how to be poker players, but because there are lots of examples in social science, particularly economics and political science, of game theory models with incomplete information. And that's what poker is in its essence. So being able to think through the data generating process for one of these non-cooperative incomplete information games is a good skill to have for understanding a good chunk of the social science literature. At the same time, I really like poker examples because they combine the randomization approach to probability with the Bayesian subjective approach to probability, because the cards are dealt randomly, but the bets are not. The bets are not randomized. They're conditional on the cards, and so they have an induced distribution. But a human chooses those, and how you update your beliefs as to what hands or range of hands other poker players have depends on your subjective mental model for how they are playing. It depends on any reads of their body language or things like that. So those play into the Bayesian subjective updating of beliefs, and also using those updated beliefs and the probabilities to make decisions as to whether to call, to raise, to fold, all those sorts of things. So it manages to get both perspectives on probability that have been, at odds with each other since the 1800s into the same game at the same time in the same homework problem. Now, if you were at UCLA, you could take an entire class that is called Introduction to Probability with poker examples. And every lecture, every homework, all they do is look at a video and then see what the probabilistic implications of that are as a way to learn the multiplication rule and the addition rule and Bayes rule and expectations and all these sorts of things. And if you want, you can get this book by Frederick Schoenberg, who teaches that class at UCLA. So it's not just me who thinks this is a good way to learn about probability, but we do more on the Bayesian side, where this is like part frequentist, part Bayesian sorts of stuff. But it's not probability doesn't come especially naturally to a lot of people. It didn't come naturally to me either. And I, like most of you, took the sequence of things like backwards. I learned how to do regression and stata and Excel like when I was undergrad, and then when I got to grad school, I actually took a Bayesian class or two without first learning probability. And it made it a lot harder, and I didn't really get it. So finally I decided, I need to take like probability 101. So I took it the summer school after my first year of the PhD program. And I would sit there and like the lecturer would like talk about stuff, and I'd be like, okay, like I got this. And then the homeworks would come, the quizzes would come, the midterm would come, the final would come, and I did not get this. I thought I did, but I didn't quite be able to get point. And I should have failed, but like, whatever. Harvard's not going to fail a graduate student in an undergraduate class in summer school. But I didn't really get it. I didn't use Bayesian stuff on my dissertation. It wasn't like that practical to do something that innovative at the time. Using Bayesian inverse because the algorithms were so limited. And it took until Stan, we started to have a vision for that when I realized, I could do all this stuff with Stan if I actually understood probability. And then I was motivated enough to like actually get it to where I can do it now. But it's not something that just, comes to a lot of people. And even though with like discrete sample spaces, small number of variables, things like that, you can sort of teach yourself how to go through problems like this. Those sorts of intuitions as they were, but even intuition is kind of a strong word. It's like once you figure out the mechanics of how to do the answer, then it's easier to understand what you were doing. But those intuitions can become non-intuitive or counterintuitive as you go to continuous spaces and multiple random variables. So you really have to rely on the mechanics of using the rules, but poker is a good, vivid way of being able to practice stuff like that. So the next, independent check model. Okay, so this is basically like, do you understand the multiplication rule? 3,600,000 something times. And you had to write half a line of code. And it took some people all week to be able to get this part here, which is we want to, so x underscore is the sorted x. X comes into this function as an unordered, but the integers say like what order they finish in. So we sort that, initialize probability to 1, and then we want to keep multiplying. So what we need to do is fish out the name of the jth place finisher. So J starts at 1. And then get that name, index stacks to get that person's stacks as a proportion of the stacks of the rest of the people who haven't been accounted for yet. So when J is equal to 1, this pulls out the name of the first place finisher, and the probability of that person finishing in first place is the proportion of total chips at the table. And then this line, which you were given, just zeroes out the chips for the person that you just accounted for. So then when you take the sum at subsequent iterations of the loop, it doesn't count that person's chips. So when J is equal to 2, we're trying to get the conditional probability for this person coming in second, given that someone else came in first. We fish out the name of the purported second place person, divide by stacks, which no longer includes the size of the stack of the person who finished first. And then we can do third conditional on someone finishing first and second, etc., to generate these joint probability of these 10 people finishing a poker tournament in this prescribed order. And then we can go over the columns of the finishes 10 matrix to calculate the probability for everything in the sample space, all 3,600,000 whatever thousand ways in which 10 people can finish in a poker tournament in a particular order. So you could do this with a loop, that would be fine. Probably like a little bit neater to use the apply function on the finishes 10 matrix. We want to apply this to the columns of that matrix. We want to apply the ICM function that we just wrote to those columns, and we want to supply the additional argument. So each column is going to be the first argument to ICM, and we want to supply the additional argument. What are the stacks that these people started the hand with before there was any betting or antes or blinds or anything like that? So this is something that you sort of apply in between hands, not during hands. And if we look at this, we're multiplying positive numbers here. So all these probabilities are necessarily positive. What isn't obvious until maybe retrospect, at best, is that these probabilities are going to sum to 1 over the entire sample space. And that's because we've applied the multiplication rule millions of times correctly in order to get that. So again, necessary and almost sufficient condition for you to do one of these problems right. Do your probabilities add up to 1? If not, you definitely got it wrong, except maybe with some rounding error or something like that. And if they do add up to 1, it's almost impossible that you could have made a logic mistake. Like, how can you add up 3,600,000 numbers and accidentally get 1 if you did it wrong? Anyway, so admissible independent chip model is actually used poker players devising strategies. The end of a poker tournament. It's a little bit simplistic, so it's kind of just a starting point, but you can still get some value added. And I wanted to point out that this problem is structurally similar to one that we talked about in the context of bowling. If you're going to think about the individual 10 pins and the event that this pin gets knocked down and that pin gets knocked down, we can write the probability of a strike as the marginal probability that the first pin gets knocked down times the conditional probability that the second pin gets knocked down given the first pin got knocked down, times the conditional probability the third pin gets times the conditional probability of the second pin getting knocked down given the first pin getting knocked down, times the conditional probability of the third pin getting knocked down given that the first 2 pins were knocked down, with the associated probabilities of that happening. And the independent chip model just assumes that those conditional probabilities can be specified by proportions. If you were doing bowling, you would want to think of like a spatial model to dictate those probabilities, but it's essentially just the poker version of a bowling thing that we talked about previously. All right, so we got that. The next of these problems are basically just about applying the hypergeometric distribution and combinatorics and using the multiplication rule and the addition rule and stuff like that. And so you can look in the answer key to see if what, oh, you had a question?
Why wouldn't it be 10 choose 3? Because there are 3 players and there's like, yeah.
Yeah, so 2 players get the kings. And then you have a conditional probability that somebody else gets the aces, given that 2 people each have 2 kings, and then there's 8 people left who could get the 2 aces. But anyway, all these next, using the hypergeometric distribution, using the multiplication rule, using the addition rule, when you have to add up the probabilities of things. And so that is just tedious, but not anything too deep in terms of concepts. So I want to go on to 1.7, the posterior probability of Mannion having aces from Labat's perspective, given that, or another player's perspective, given that Mannion bets. And then the other part of it was a little bit harder, the posterior probability that Mannion has a pair of aces given that he bets and that Labat has 2 kings. And so the problem specifies, okay, there's 52 choose 2 possible poker hands, and this, it's stated here so you could use it. They've done simulations and whatnot, and so when there's a lot of people at the table and you have to go first, which is in general a disadvantage because everyone else can condition on you and you can't condition on anybody else yet. And except for the blinds, you're also going to have to go first in any subsequent rounds of betting. So you're at a first mover disadvantage. And so you need a really pretty good hand in order for the expectation of raising to be better than the expectation of folding. And the break-even point is basically, the 14th% best hand sort of makes you about indifferent between raising and folding when you have to go first. Okay, so that's an approximation. That's a mental model. That's assuming Mannion is not crazy, but that's the sort of things that poker players are thinking about. And so in order to do one of these problems, we have to figure out what's the prior probability of Mannion being dealt a pair of aces. And then we have to figure out, even though it shouldn't have taken more than 5 seconds, what is the probability that Mannion would bet given that he was dealt 2 aces, which is 1. You're going to raise every opportunity you get pre-flop if you have a pair of aces, because you cannot possibly be behind anybody else. So it's in your expectation to just at least raise a little bit every chance you get. And then the denominator is the proportion of hands that you raise. So it gets a little bit harder when you also condition on the fact that Mannion has 2 kings, and so Labat has 2 kings. And so from Labat's perspective, the deck only has 50 cards left in it because 2 were taken out. And so now out of a 50 card deck, what's the prior probability that Mannion is dealt 2 aces? That's going to be a little bit higher than it was in a 52 card deck. Still, Mannion is going to bet if he has those 2 aces, irrespective of whether somebody else has kings. But he doesn't know the other person has kings, so you can't condition on that anyway. And then the probability in the denominator is a little bit smaller, because the fact that Labat has the king of diamonds and the king of clubs eliminates some of the hands that Mannion would have raised with. So any ace with the king of diamonds, Mannion would have raised, but he can't have the king of diamonds because Labat does. Same thing with the ace and the king of clubs, so that's out. The king of diamonds and the king of clubs can't have because Labat has that. King of diamonds with any queen would get raised, king of clubs with any queen. So anyway, that eliminates like 17 of the hands that Mannion could have raised with. And so the probability that he's has, posterior probability that he has a pair of aces goes up a little bit if you condition on the fact that Labat has 2 kings, but it's still pretty small. So if you're Labat, if you're Zhu, you think, in all probability you're ahead of Mannion when you have 2 kings. Right? So that's sort of bringing in the Bayesian aspect of it, given that he bets. Changes the probability. So then Zhu's decision, kind of regret putting this problem on here because people spent a lot of time on it when really we were just trying to get an example. So I had a point, but I don't know if the point was worth the amount of time that people spent on it. So what the question asks is just give an example of 3 plausible probabilities for what happens when Zhu goes all in. So either everybody's going to fold, in which case Zhu wins, but doesn't make very much, or someone's going to call, in which case Zhu could lose, in which case he'd be out, or Zhu could win, in which case he'd have approximately double the number of chips that he started the hand with. And so that gives us 2 constraints. The probabilities need to sum up to 1, and then the other thing, the constraint the question gives you, is like choose plausible probabilities such that the expectation number of chips that he has afterward is about the same as the number of chips he has before. And so this basically defines a break-even point between going all in and folding with a pair of kings. So an example of that would be 82.5% that everybody folds, 17% chance that he gets called and loses, and a 0.5% chance that he gets called and wins. That would give him expectation basically the same number of chips that he has now. And then you look at it and you might, or if you didn't, that's okay, but you would if you had played poker before. The Zhu's probabilities are more favorable than these here, which give him basically breaking even. So more than 82.5% chance that everybody's going to fold, less than 17% chance that he's going to lose, and small but bigger than 0.5% chance that he's going to get called and win, given that he has a pair of kings. And so the point that I wanted to get with this is that oftentimes when computing these expectations to decide what to do, you don't have to do it super exactly. You just have to figure out, okay, what's the break-even point, or what's a break-even point, and which side of the break-even point am I on in order to figure out. And so here, clearly, going all in is better in expectation than folding with a pair of kings, which would just be insane. Only question is whether it should go all in or bet a small raise.
I was just wondering, you said on Campus Wire that there's like a infinite amount of answers hypothetically, but I guess is infinite if because you said they're kind of like bounds of what is like reasonable to expect there. So one that is conditional on you somewhat knowing the game, but let's say that what those baskets are, you would have an infinite amount of options if okay, because it could be like 82.5, 82.5 point, and so forth.
So all of those are fine.
But if those were discrete, so like 82 or 83%, then your amount of answers to this would be given by the baskets, right?
Right. Yeah. One basket, fall in one basket.
I guess my question is, given that his probability is near 0 of winning in a showdown, well, how is this an example of a plausible set of probabilities? Because if he has pocket kings, his chances of winning couldn't be that small.
Oh, right. So 0.005 is the probability of getting called and winning. So if he's getting called, it's probably going to be with queens or kings or aces or ace king. So given that he's called, he's going to have maybe 40-50% chance of winning. But the probability that both of those things happening, getting called and winning, is still going to be pretty small. But it's way bigger than 0.005. And the probability of losing is way less than 0.17. So he's way on the one side of the break even. If you use this or something similar, or really like there's no set of probabilities you could choose in which he's on the fold side of the break even point there.
Why wouldn't the payout for losing be negative 24 million?
Well, so you could do it either way as a level. So here I'm saying if he loses, he's going to have 0, and so he's out. If he wins, he's going to pick up the 49 and what he all-in with, and if he gets called, he's going to pick up the 49, the however many he went all in with, and the equivalent number of chips of the other people. So I did this in levels, but you could do it in differences. In which case, keep going.
So practically speaking, one thing is that it seems like he did actually the right thing by going all in, and yet he was vanquished, and maybe there was a small chance of that happening, and yet it happened. So how do you optimize, I guess, in this game? And second thing, as a player, you would have to calculate this in your head, pretty much.
Mm-hmm.
Is that practical?
So what professional poker players do when they're not playing poker is they are on their computer and they're doing simulations and they figure out all these things and they memorize it as much as they can as to what to do in different situations. So yes, and they're approximating, obviously, because they can't have their laptops or whatever with them. Yes, they're not going to be able to calculate this stuff exactly. Zhu's decision was entirely plausible. He didn't have that many chips relative to the other people. It's really only a question of should he raise a small amount or should he raise for all the chips. Case could be made for raising a smaller amount so that the probability that everyone else folds is less, probability they call is higher, and so you stand to gain more later. But if he didn't go all in before the flop, he probably would have gone all in sometime afterward. Yes?
So in the video, when he goes all in, he has there is a small percentage when there's computing.
Yeah.
He has 0 probability of winning, whereas Labat has 2 or 3%, and then the other guy has 95 or something. Mm-hmm. Why at the beginning Zhu has 0 probability of winning, even though he has the same 2 kings as the other?
He could get a straight flush to the king.
Okay.
Opportunities to get a straight flush to the king. That would be the only way he could win. So that's why it was 0.0, because they can only put 1 decimal place on the screen. But then after the first 3 cards were revealed, it was 0. So anyway, yeah, straight flush. That's about all. Or he could tie with the straight to the king. Okay, so the very interesting decision, not so much Mannion's second decision where he's going to go all in, obviously, which was Labat's second decision after Zhu and Mannion had gone in all in as to whether he should call again with his pair of kings. And so to answer a question like this, you have to think about the different scenarios. There's a few scenarios, but the 2 that we're asked to consider are, well, if he folds, then he would still have almost 50. Labat would have almost 50 million in chips, and then Zhu and Mannion would have pot, and then but most likely, given that Mannion called, he's going to win that. So that would be one scenario, and then Zhu would be eliminated. Mannion would have 77 million, something like that, chips. And then they would keep playing, or they come back in 2 days and they keep playing. And then the other scenario is what actually happens, which is Labat calls, Mannion beats both of them, and Labat only has 8 million chips left, and Zhu is out. So in order to make that into expectations for prize money, we have to get, what are the prizes for finishing in this. And we're going to want to apply our ICM function to now the 9 ways that the people left can finish. And in each of those 2 scenarios, the stacks are going to be reallocated from what they were at the beginning of the video. So you get the stacks right for those 9 people. Apply the ICM function again to get the probability of this or that finishing order. And you multiply them by prizes, which is a vector of how many millions of dollars in cash that you win for finishing in these different places. And then you take the row that corresponds to Labatt in the matrix of finishes, and then that's going to get expanded out to like 300,000 something, all of which are weighted by the corresponding probabilities of those happen, which again, the probabilities are going to add up to 1. So this gives us an expected value for what if Labatt had folded of 3.5 million. Okay. So then we do the same thing for the second scenario where he calls and loses. So he only has 8 million chips left. Get that expectation 1.65 or something like that in expected value. So he's probably going to come in 9th, but has a slight chance of finishing a little bit better than that. But in order to judge whether this is a good or bad decision, you're going to have to consider, even though the homework didn't ask you to, additional scenarios. And there's like a few because Zhu could win the main pot. But the main one to consider is, well, what if Labatt calls and wins both of the pots? In which case, he would have 120 million chips, and both Zhu and Mannion would be eliminated, and then everyone else would have, whatever. So we calculate up the expectation again, and it's 5.3 million. And so basically speaking, Labatt's decision-making thing is, okay, I could have an expectation of 3.5 million if I just fold. If I lose to Mannion, then I'm going to have an expectation of 1.65 million. And if I call and I beat Mannion and Zhu, I'm going to have an expectation of 5.3 million. So then you ask yourself, okay, what probability of winning against Mannion does Zhu need for the expectation of scenario 2 and scenario 3 as a function of the probability of winning to equal the expected value under scenario 1 where he folds. And so he's going to need like a 0.5 probability of winning when he calls for this to be a good decision. And then you have to consider, well, what's the probability of Labatt winning along the horizontal axis there in order to figure out which side of the red line you're on. And for that, you have to basically consider Labatt's perception of Mannion's perception of Zhu. So let's suppose that when Zhu goes all in, Mannion would call with either a pair of queens or a pair of kings or a pair of aces. So there's 4 choose 2, which is 6 ways that Mannion could have a pair of queens. One way to have the other pair of kings, given that Labatt has those 2 kings already, or the other 2 kings already. And then there's also 6 choose 2 ways that Mannion could have a pair of aces. But if Mannion is going to call with a pair of queens or a pair of kings or a pair of aces, then the probability is going to be right at 0.5, because if Mannion has a pair of queens, then Labatt is way ahead, and there's a 6 out of 13 chance of that. If Mannion has a pair of aces, then Labatt is way behind, and there's a 6 out of 13 chance of that. And then there's a 1 in 13 chance that Mannion has the other 2 kings, in which case it's good to call, because even though they would tie if they beat Zhu, then they split the chips that Zhu bet. So if Mannion is going to call with a pair of queens or a pair of kings or a pair of aces, or maybe also like ace-king of the same suit, then the probability is going to be greater than 0.5 for Labat. But if Mannion is only going to call with a pair of kings and a pair of aces, then it goes the other way, because there's a 6 out of 7 chance that Mannion is way ahead with a pair of aces, and a 1 out of 7 chance that they're, tied, because they both have the pair of kings. And so then it, pushes back the question again: is Mannion going to call with a pair of queens, or just a pair of kings, a pair of aces? And for that, you didn't have to do it on the problem, but you would need to think, when is it in Zhu's expectation to go all in? Would he do it with a pair of jacks? Would he do it with a pair of tens? If so, then the optimal strategy for Mannion would be to call with a pair of queens. But if not, then you sort of have to call with fewer hands. Anyway, it didn't ask you to get into all that, but that's how you would think about trying to decide whether this is a good decision or a bad decision. And the whole internet hasn't been able to figure that out in a year and a half. It's extraordinarily close, like basically has the same expectation between calling and folding, but the variance of the chips if he calls is huge in terms of the amount that's going to be shifted around, and so that makes it a very stressful situation to be in. And finally, on this, I think it's worth mentioning. What would Fisher say about this? So I don't know if he ever wrote about poker, so I might be putting words in his mouth. But the only thing, if he were being consistent, that you could say validly, which is to say objectively, about the probability Mannion is dealt 2 aces, given that Labat has 2 kings, is what we calculated up in a few subproblems ago. That comes out to something like 0.005. If you just limit yourself to what can be said objectively, okay, he has like a 5 in 1,000 chance of having a pair of aces. If I'm Labat and I have a pair of kings, then in all likelihood I'm ahead. This is an easy call. And it would be preposterous to introduce subjective things like a mental model of how 2 other people are playing, trying to read Mannion's body language when he takes like 4 seconds to go all in when Zhu bets 25 million chips into him. Those sorts of things, those are subjective. And at least if this were like science policy running public companies, you can't be subjective, according to Fisher. But according to anyone who has ever played poker, Fisher is being preposterous. If Labat has a 0.5 chance of winning here, which is to say, like, what's the probability that neither Zhu nor Mannion has a pair of aces? Like, if that's 0.5, it's got to be somewhere around there. 100 times bigger than the objective, probability. But, assuming the people who got to the last 10 out of like 7,500 people of a poker tournament are not just like irrational, crazy people, Mannion is not going to have a 7 and a 2. So, and Labat knows it. I mean, he knows he might have a 0.5 chance at best chance to win. Yeah.
To ask about, I wanted to defend Fisher a little bit because all of the signals that were being sent here with the interactions of Zhu, Mannion, and Labat are interpreted as positive signals, while on the other hand, it could entirely be the case that one of them is utterly bluffing and just trying to scare other guys off. Why are we not considering this possibility? And I think that Fisher's reasoning would prevent us from this subjective interpretation of signals one way or the other and just depend on objective probabilities.
So if poker players only considered the objective probabilities of cards being dealt, given the cards that they can see, then there would be no bluffing. And there is, and it's a strategy which basically says to bet in such a way that it doesn't really matter what two cards you actually have. It just matters, the expectation over the possible hands that you have that are not ruled out by the way that you've bet. And so that would be something to consider if we were to consider poker more seriously. I would say in defense of this, which was already difficult enough, I didn't want to go there, but also there's limited ability to bluff all in before some of the cards in the middle are dealt. There is not a whole lot of room for that to be positive expectation for somebody. Now, when the fourth or the fifth card comes, and so more clearly what your showdown hand is going to be, then the strategic value of bluffing comes into play more. But on the other hand, if we were to consider all of those things, and somebody were to play poker and be like, I'm not going to use anything subjective, I'm just going to use the probabilities from the cards, they would in expectation be making less money because they would not bluff and they would just lose whenever their cards are worse than somebody else's. So I still think both the randomization of the cards and the updating of your beliefs based on subjective interpretations of what's going on around you with data are both essential for understanding poker. Okay, next question about bowling. So prior choice of mu, something small. Remember, it doesn't have to be an integer. Anyway, I got Poisson prior probabilities for the epsilon that look like this. Okay. We talk when we do this before about multiplying prior probability by probability of the data given the parameters, and that's sort of the abstract way of thinking about these things. When we do it on a computer, we're not multiplying probabilities. We're adding logarithms of probabilities, or adding logarithms of probability densities that don't have to be probabilities in order to calculate these things accurately on a computer without having underflow where it gets so close to zero that the computer just treats it as zero, or overflow where sometimes numbers get so close to infinity that R just treats it as infinity, and those screw up your calculations. But even in the interim, you can get inaccurate results if you don't think about these things. Anyway, we can take the logarithm of the Poisson PMF pretty easily and add it to the log probability under this Bell number ratios thing. So different people had different bowlers, different data, and different realizations. I used this one for someone named Melania Rossi. And so the data looks like this. Source in the thing, and the arguments to the log PR function are x, the number of pins, and the number of pins available, and what value of upsilon to use. And so you just set yourself up with a range of upsilons. Technically that could go off to infinity, but really you only needed to run it up to probably about 20 or so, because the Poisson, if you have a small mu, is going to concentrate almost all of the probability into numbers that you can count on your fingers. But anyway, we can get the logarithm of the prior if we specify log equal true to the Dpois function. We can get the log likelihood of the first roll of the first game by applying to this vector of upsilons our log PR function. Add those two together to get the numerator. And then you could just anti-log that and sum it to get the denominator, and that would be fine, and it actually works well enough. But if you had more than a few dozen data points, then you're going to have to worry a little bit more about this. And I linked to a blog post saying, here's the most accurate way to calculate these things, and it's done by shifting according to the maximum value of the log numerator before you sum it up to get the denominator and you divide to get the posterior. So we'll talk more about stable numerical computation, but you might want to check out that blog post. Anyway, the one that I hoped everybody could get to was when you update your posterior distribution after each game. And so you could hard code this, but it would be pretty tedious. It's a little bit easier if you write a function that would take a matrix of, you know, when the pins got knocked down and how many of them, and evaluated that log likelihood. So here we have, you know, for all the first rolls, they all have n equal 10. So we can just, you know, take the first column of that. Otherwise, for the second rolls, we have to loop over the frames, you know, check whether it's in A or not, evaluate the conditional probability and take the logarithm, keep adding it to what we had before. And then the 10th frame has special rules depending on whether you get 1 or 2 or 0 extra rolls that you have to add on to all this, and then you return the log likelihood at the end. Then we can call this function to get the numerators after each of the 6 games by basically s applying to upsilon the log likelihood function. For the first game, we want to add the log prior as well. And in subsequent games, we just add on to the log numerator from the previous games, because that's all going to have the log prior built into it. Still do this numerical stability thing, even though if you didn't, that was fine on this homework. And then, you know, how can we show how these posterior probabilities change if we condition on first and second game, first and second and third game, etc., all the way up to 6. So I did this with ggplot here, and you can see after 1 game, we're still like have, you know, some positive probability that upsilon could be as much as 11. Doesn't change a whole lot for the second game. But once we get to the 3rd game, 4th game, 5th game, 6th game, these beliefs about what Melania Rossi's upsilon is change a lot from what the prior that we started out with them was. They get shifted over more towards smaller numbers. They get concentrated more. And, you know, by the end of 6 games, it's essentially, you know, almost definitely going to be either 1 or 0. And there's twice as much probability that it's 1 than 0.
So how do we explain the non-linearity of the updating? Meaning that, like, at the beginning it's kind of slow, but like for instance between like 3 and 4, like there is like a huge spike into the probability of like the parameter being 1.
These don't change uniformly. So you might say, okay, in every game there's 10 frames, so there ought to be more consistent change. But in the second game, she did her worst. So, you know, she had a decent game the first one and then like a bad one the second time. And so under like Bayesian updated, there was sort of like conflicting about what, and then got in a rhythm or whatever for the remaining games, and it started to change more because there was just like strike, spare, you know, sorts of things. So if you got to see that, that's good. And if you get to check out the answer key, that is almost as good to see, you know, the evolution of these things as we condition on data. And so, yeah, your posterior expectation of Rossi's epsilon would be, or upsilon would be, you know, 0.7 or so.
Wondering, like, what we should present when asked to provide a posterior prediction of a distribution. Do we just want the point value and some measure of variance? Do we want something else? And then the other question I would ask is this answer key going to be uploaded?
Yeah, I'll upload it. It already is. I just need to move it to where you can see it. So yes, so Bayesian, in terms of summarizing the results, it's going to have more emphasis on graphs than on one number, because technically your answer is the whole posterior distribution. And so, like, whether this is 0.6 0.22 or 0.623 or whatever is not that important. It's the more qualitative thing that like this is twice as much as 0. So there's more emphasis on graphical summaries. So we'll talk more about that. Also, much more favoring posterior expectation, posterior median at the expense of posterior mode, which is almost completely a red herring. But it's something that people think, oh, like this is the most likely thing. But Bayesian approach really emphasizes functions of the whole posterior distribution, not just one point. Anyway, okay, enough about that. You can check out the answer key. Let's talk about Bayes' rule with continuous random variables a bit more. So, disclosure, this is Columbia, use it for research, use it outside of Columbia, creates the appearance of a conflict of interest. I also feel the need to say I don't have a conflict of interest with a company called MAP Biopharmaceutical, which is an example we're going to use today. Although pharmaceutical companies love Stan, they've contributed money to develop things in Stan. They've had their own employees contribute things to Stan, and that does not create a conflict of interest at all. So let's just review and extend some ideas that we were talking about on Tuesday. Here I'm plotting the CDF of the logistic distribution, which is defined on a space of all real numbers along the horizontal axis here. And like a lot of CDFs, it has this sort of S shape because the vertical axis is constrained between 0 and 1. So if you have a random variable that's defined on the whole real number line, and then the output of it has to be between 0 and 1, eventually, and this has to be an increasing function because it's a CDF, eventually it has to like flatten out at the extremes. And that's what this does here. The CDF of the standard logistic distribution is given by this function here, 1 divided by 1 plus e to the negative x for any real x. Now, if we took the derivative of the black curve here, we get the PDF in red. It's defined over the same space, all real numbers. And this is symmetric, so it looks kind of like the normal distribution, but it's going to have thicker tails. So unlike the standard normal distribution where you have a very small probability of getting anything greater than 2 in absolute value, you have decent chance of getting -3 or something under or even more extreme under a logistic distribution. If I differentiate the CDF, the function that I get for the PDF is given here. We see we have a mode at 0, which corresponds to the point on the CDF where the slope is the highest, etc. So that's basically what we were talking about on Tuesday. It's just this is a different distribution called the logistic one, and we'll see how it's used in logit models in a few weeks. Okay, so everybody comfortable with that based on what we did last time? No? Okay. Now, what's a little bit new is, okay, this CDF is an increasing function. So therefore, the inverse to the CD function has to exist. And the inverse would conceptually be, okay, if I start over here on the vertical axis, it's some value between 0 and 1, go over the curve down to the horizontal axis, I would have an inverse function, a mapping from the 0-1 interval to the entire real line. And the fact that this is an increasing function implies that a unique inverse function exists, even if we can't represent it in elementary terms. But in this case, we actually can. So if like p is equal to 1 divided by 1 plus e to the negative x, then x is equal to the logarithm of p divided by 1 minus p. And we see over here in green the inverse function of the CDF in black. And this green function is called the inverse CDF, or it's also called the quantile function. It's a function from the numbers between 0 and 1 to the sample space of the random variable. And so If I was like right here, 0.25, I go up, over, whatever that number is referred to as the 25th percentile or the first quartile, whatever number that is, such that 25% is going to be less than this number. So questions about the green line? It's the inverse of the CDF. And one thing that this is useful for is if you wanted to generate a random number from the logistic distribution, you could take a random number from a standard uniform distribution, which puts you somewhere between 0 and 1 on the horizontal randomly here, up to the curve, over to the vertical axis, and you get a realization of the logistic distribution. And this is a very nice way to generate random numbers. Take a random number from standard uniform and apply the inverse CDF to it. In here, at the bottom in blue, we have the derivative of the inverse CDF, which is sometimes known as the quantile density function. It's not useful for that much, but it's the slope of the quantile function, which gets really steep at the endpoints in this case, more flat in the middle. And although it's not so clear here, the reciprocal of the quantile density function in terms of p is equal to the probability density function. But anyway, the main ones that we want to focus on are not the blue one. It's the black, which is the CDF, the red, which is the PDF, and the derivative of the black curve, and the green, which is the inverse of the black curve. Good with that? Okay. All right. So where does MAP biopharmaceutical come in? Those of you might remember in 2014, we had another outbreak of Ebola in Africa. And 7 people from like the United States and Europe who were with like Doctors Without Borders and stuff like that went to West Africa to try to help, contain the Ebola epidemic. And 7 of the many people who went over there themselves got Ebola. And so then they got sent back to the United States, and it was on CNN and whatever. And those people who were doctors and nurses got infected with Ebola, and then they were given experimental drug, which was being developed by MAP Biopharmaceutical. The drug is called ZMapp, and the goal of what we're going to try to do today, maybe also on Tuesday of next week, is to decide whether the ZMapp drug is effective at curing someone with Ebola. So in this case, we have 7 people exposed and take the drug. Binomial distribution is pretty standard for something like this, for the probability of observing Y survivals out of N people who take the drug. If the common survival probability is pi, and that is given by the binomial probability mass function that we learned about last week. And for observed Y, we can write what's known as the log likelihood function, which is the logarithm of this, considered as a function of pi, and so we're allowed to ignore any constants like the n choose y business, which does not involve y. Anyway, the logarithm of that function is given here. If we were doing this in Stan, we would want to be dealing with the logarithm of the binomial PMF rather than the binomial PMF itself. Okay, so everybody kind of understand? We're trying to figure out if this drug is effective. So in trials conducted by MAP Biopharmaceutical with 21 subjects, it was observed that 14 survived to the end of the study and 7 didn't. So basically, it depends on the strain, but if you didn't have any like special drugs, if you just had like the standard treatments for Ebola that they had at the time, you would have like about a 0.5 chance of survival. So they did, a small study, 21 subjects, and who took the ZMapp, and then 14 survived to the end of the study and 7 didn't. And so that's our sort of trial evidence. So what might you think it would be kind of a reasonable prior information as to the survival probability when actually 7 doctors get Ebola while trying to contain it. What might you think would be like prior mean, prior median, something about that based on the trial evidence? Which is 14 survived, 7 didn't.
So number 14.
Hmm?
So number 14, the chances you're gonna make it.
Right. So if we took it literally, it'd be 14 out of 21. But there are lots of things that are different between a trial and the real world. One of which is the fact that out of the 21 subjects in the trial, 21 out of 21 were monkeys. What do you think is the prior probability that the drug is going to cure a human who has Ebola, based on the trial evidence? Go ahead.
I actually would just keep it at 2/3 because I don't know that monkeys would stand a greater or lesser chance of responding to the drug than humans.
Plausible. Certainly the reason why when doing trials we don't force somebody to get Ebola in order to then see if the drug is effective, and they test it on animals, particularly monkeys, is because in other situations biologists and whatnot have noticed that the immune system of monkeys is very similar to the immune system of people, and so it sort of gives us the best comparison.
So 7 out of 21 isn't that necessarily that strong evidence. It's a small sample, so for me it would probably be somewhere in between 1/3 and 1/2. Like I would do some kind of weighting between the two.
Right. Also plausible. Okay, but it's 14 of the monkeys survived and 7 didn't. So you might be about 0.6 or so. Yeah. Other question?
Do what you just said, that we'll just multiply the prior of how much usually monkeys survive in other experiments, and then what's the ratio of humans application to those kind of drugs, and find that probability, multiply by this 14 out of 21 to get the answer.
Could do it that way. A little bit assumes that, well, you'd have to come up with some sort of adjustment to reflect your uncertainty as to whether this is going to work with people after doing it.
Maybe we can start with uniform distribution, or try to use the uninformed approach, calculate Jeffrey's prior or something like this.
So I think in this situation, particularly when we're dealing with small numbers, we don't want to go with a super uninformative prior. So one thing is, and I didn't explain this yet, but the drug is made from plants, so it's not very likely the drug will kill you. Like if you had a 0.5 chance of surviving, with just no special treatment or whatever, and then you took a drug, it's organic, your probability of survival is probably not going to go to 0.03. So and also Ebola is notoriously difficult to treat, and so the chance a priori that this is going to cure 99% of people is also not particularly plausible. But if we just did a flat prior over the whole 0-1 space, that would imply that 0.01, which is to say there's a very high chance the drug kills you, and 0.99, a very high chance that everyone is going to get cured, are just as plausible as 0.5, which would be if the drug didn't really have any effect at all. So I think medical professionals or whatever their informative prior would be a lot closer to 0.5, and that would be a lot more useful for deciding whether this is effective when you only have a few monkeys or a few people's worth of data to evaluate it on. Okay, uniform distribution. So it's defined between 0 and 1. It has PDF that is equal to 1 as long as x is in that interval. The CDF is equal to x, and the expectation you can work out is equal to 1/2. I'm not going to go through the steps of that. what I do want to go through is, okay, if x is distributed standard uniform, and z of x is a function that is equal to a plus the quantity b minus a of x, what would be, let's say, the PDF of z? So what's the three-step procedure for solving a problem like this? Or what's the first of the three steps? All right, so we want to express x as a function of z, which would be some hardcore algebra here.
C minus A.
Okay. So if that's the transformation, then the CDF of z is just going to be the same as this. Right, so, well, you can't really see, but what I'm writing here is z is a function of x. So, okay, the CDF is equal to this. And now if we differentiate that CDF with respect to x, then what would the PDF of x be? So if we consider this as a function of x, then the derivative is just going to be 1 over b minus a. So the uniform PDF, it's going to be flat, but instead of between just the 0 to 1 interval, it's going to be in the interval between a and b. All right. Okay, so you could get the expectation and whatnot. We already talked a little bit about uninformative priors. And so next question, let's say z of x is inverse CDF, quantile function of x, where x is distributed standard normal. So if z of x is the inverse CDF applied to x, what is x as a function of z? What's the inverse of an inverse CDF? CDF. All right, so then to get the PDF of x, we take the probably PDF of standard uniform, which is just 1, and we multiply by what? What's the third step? We have to multiply by something? Like the derivative of the transformation from z to x? Right. So what's the derivative of f of x? Capital F of x. Little f of x. Right. So z is going to have PDF, whatever is the PDF that corresponds to the inverse CDF that you were using. So like if we go back to in green here, all right, so green is our inverse CDF. We're going to take a standard uniform along the horizontal, map it to all real numbers in this case by going like this. And so that result, it's going to have the PDF in red here, because this is the PDF that is the derivative of that CDF, and that CDF is the inverse of the quantile function. Goes the other way. So that's another way of saying that you can generate a random variable from one distribution by taking standard uniform and transforming it with the inverse CDF of whatever distribution you want to. So how does this help us? And we're running out of time a little bit today, so we'll pick this up more next week. But it's a little bit weird, in my opinion, that only in the past few years have researchers started to think about, well, what would be good distributions for specifying priors with? We have all these distributions for data, but none of them are really created in order to specify informative priors over a parameter space theta. But that has started to change a little bit in the past few years with the introduction of so-called quantile parameterized distributions, which are basically distributions whose parameters are quantiles, and quantiles are relatively easy to specify in priors. In particular, this paper by Hadlock and Bishop derives some important quantile functions for two cases, one of which we'll talk about today and the other which we'll talk about on Tuesday, in the case where the parameter space has lower bounds and upper bounds. In this case, it'd be 0 and 1 for survival probability. And in order to specify this prior, you have to specify three pieces of information: a lower quantile, a median, and an upper quantile. So alpha can be whatever, but let's just say it's 0.25. So if you were to specify this prior, you would say, okay, here's the 25th percentile that I think, here is the median that I think, here is the 75th percentile that I think. And the quantile parameterized distribution that Hadlock and Bishop derived based on the Johnson system, which you don't need to know, generates that distribution for you. So what would it look like? I forgot to upload this, but it's a stan file, and you can define your own language functions in the stan language, and then export them to R. So this inverse CDF function that I was talking about, after it gets translated to C++ and compile, now exists in R's workspace, and you can call it. So this is a function of a cumulative probability. You need to specify what alpha, the lower quantile, pertains to, in this case 25%. Need to say what the lower bounds of the thing you're talking about is, in this case 0 and 1, because it's a survival probability. And then you need to give it the three quantiles: 25th percentile, 50th percentile, 75th percentile, let's say. And what I'm saying is if you say, okay, I think there's a 25% chance that the survival probability is less than 0.4, and I think there's a 0.5 chance that it's less than 0.55, and greater than, and also a 0.5 chance it's greater than 0.55. So maybe a little bit of evidence from the monkeys that this is going to work well with people. And I think there's a 25% chance that the survival probability is greater than 0.7. I could say something like that. You can say anything you want, but what I am saying is that if you supply those three pieces of information and the fact that this survival probability is logically bounded between 0 and 1, Hadlock and Bishop can construct a quantile function which defines a prior distribution you can use that is an increasing function of the survival probability that goes through exactly the 3 points that you specify. And this is a prior distribution that I think is relatively easy to specify, relatively easy to update when you get more information, as compared to what people have done since like the 1990s and earlier, where they say like, what's your prior expectation? What's your prior standard deviation? And all these things, you're essentially asking someone to do an integral in their head that we probably can't represent in explicit form even on a computer. So like, why would you anticipate that they're going to be able to give you meaningful information? Or this idea that like, if you want to elicit a prior from an expert, you like climb to the top of a mountain and then you talk to some old guy with a beard and he like tells you what prior to use. And like, whenever you do that, you get to the top of the mountain and you find like the wise guy doesn't know probability. So you're like, why am I even at the top of this mountain? And so these quantile parameterized distributions, because they don't involve like doing integrals in your head, it's just like, what's your over under? That's like the prior median. Okay, if you wanted to have 3-to-1 odds, like what would your 25th percentile and your 75th percentile of this thing be? Okay, give me those 3 pieces of information. I will supply the fact that probabilities are bounded between 0 and 1, because the wise man on the top of the mountain didn't know that. And we can literally make a increasing black line here that goes through those 3 points, and it uniquely defines a probability distribution we can use as a prior, and it works great with Stan. And we can also do this if it's slightly different, if it's just bounded on one side. There's a different quantile parameterized distribution for that, but you still have to supply the same 3 pieces of information: median, 25th percentile, 75th percentile, and lower bound. There's a different thing that you can do if the variable is unbounded, all real numbers. In this case, you need to give it median, 25th percentile, 75th percentile, and 1 more, because you don't have the bounds. So maybe like 90th percentile. But those 4 pieces of information, we can run a black increasing quantile function through this that defines a distribution, and it matches up with the prior information that you get. So we'll talk about that more as we go along, but in my opinion, this is the way in which priors can be specified more easily in the future by using this representation, the quantile function, the inverse CDF, to specify priors, and the PDF to specify the conditional distribution of data given the parameters. And both of those can be made to work with Stan. Okay, so that's it. Catch up on the reading if you're behind on that. But we'll start talking next week more about sort of principles of Bayesian inference and what we're trying to do with all this like probability and math that we're updating with. So that's that.